Hey everybody! Today's lesson is a continuation of the probability lesson that we did last time, and we're just going to extend it a little bit. Today we're going to talk a little bit about how you find probabilities when you have multiple trials. So instead of just like rolling the die one time, you roll the dice twice, or instead of picking one card, you're choosing two cards or something like that. And I wanted to start out with just a review of the fundamental counting principle because that's actually going to come in kind of handy today. If you recall the fundamental counting principle, this is the principle that we kind of figured out when we did that barbecue problem. And in the barbecue problem, we had a choice of drinks, and there was two choices of drinks, lemonade or root beer. And then we had a choice of sides, and there was two choices of sides. That was chips or potato salad. And then we had a choice of an entree or a main course. And that was either a hamburger or a hot dog or a veggie burger. And so there were three choices there. And we decided if each choice was an event, then the number of possible outcomes for these three choices is 2 times 2 times 3, or there's 12 different options there. There's 12 different kind of like combinations of or meals that you could put together with a drink, a side, and an entree from these amounts of choices. That's called the fundamental counting principle. So if you have different numbers of ways that events can happen, you multiply them together to get the number of ways that all of those events can happen. So the fundamental counting principle goes something like this. If there are m ways, this is just a variable, there are m ways that one event can occur and n ways that another event can occur, then there are m times n ways for both to occur. In other words, you're just going to multiply the different options for each event to get the total number of options for all of the events, like we did in the barbecue problem from earlier this week or last week. Okay, so we're going to kind of take that idea and we're going to slowly transition into probability idea. But let's just start with events and outcomes first, okay? So we're going to consider an experiment consisting of 2 consecutive trials of drawing a card from a standard deck of 52 playing cards. The first card is replaced before the second draw. How many possible outcomes are there for this experiment? So if you think about, there's 2 events, right? Event 1 is choosing a card, and event 2 is choosing a card, because we're going to do it twice. For the first event, there are 52 options, because there's 52 cards to choose from. So this is event 1. Event 2 is choosing a card, or I guess you could say, trial 2 or something like that, is also choosing a card. And since we put the first card that we chose back, we still have the same 52 cards to choose from. So just like we did with the 2 options, 3 options equals 12 possibilities for the barbecue, we're just going to do 52 times 52 to give us a total of 2,704 different possibilities for drawing 2 cards. So that could be like King of Diamonds, Ace of Spades, King of Diamond, 3 of Clubs, King of Hearts, 2 of clubs, or something like that, right? All the different possibilities for drawing 2 cards. This is how many there are. Okay. Now let's change the type of event we're looking for. Let's change the event a little bit. Okay. Imagine that you're trying to draw an ace on the first draw and a king on the second draw. How many possible outcomes are there where you draw an ace followed by a king? Okay, so event 1 is drawing an ace, and event 2 is drawing a king, and we just want to think about how many different ways are there for those events to happen. Well, there's 4 ways to draw an ace, because there's 4 aces in the deck, and then there's 4 ways to draw a king, because there's 4 kings in the deck. So then there are 4 times 4, or 16 ways to draw an ace and a king. So that could be like Ace of Spades, King of Clubs, or Ace of Spades, King of Diamonds, or Ace of Spades, King of Hearts, or Ace of Diamonds, King of Hearts, or whatever. There's 16 different possibilities there. Okay, so those are not probabilities yet. Those are just number of different outcomes. But if we combine those 2 ideas and combine the fundamental counting principle with the idea of probability, then we actually will get a probability. Okay, so now we're combining these 2 ideas, and we want to find the probability of drawing an ace followed by a king for 2 consecutive trials of drawing a card from a deck of 52 playing cards. assuming the first card is replaced. So if you think about the probability formula that we talked about, probability is all the ways of getting the outcome that you want divided by all the possible options. So the probability, this is how we would write this, ace, probability of ace and king, which means in 2 consecutive trials pulling an ace and pulling a king in that order, there is 4 out of 52 ways times 4 out of 52 ways. Right, there's 4 options for pulling an ace out of 52 cards. You put that ace back, assuming you pulled it, and then there's 4 options for pulling a king from those 52 cards. And you get 16, this number, over 2,704, which is this number. So it's when you're talking about a probability with multiple events or multiple trials, it's kind of like the fundamental counting principle on the top to get the number of ways to get what you want, and then the fundamental counting principle on the bottom to get the total number of outcomes. Right? So it's kind of like doing this idea in the numerator and in the denominator to get this fraction. Now this actually simplifies. This comes out to 1 over 169. So we'll probably leave it as a simplified fraction. Okay. Now these events didn't affect each other. Drawing the first card doesn't affect drawing the second card because of the replacement. So this next little statement talks about the term for that kind of scenario. Because the first card was replaced before the second draw, the 2 trials are considered independent events. Okay. 2 events are independent if the occurrence or non-occurrence of one event has no effect on the likelihood of the occurrence of the other event. Okay, that's kind of wordy. It's kind of a mouthful. But the idea is the first card draw does not affect the second card draw. Right? Assuming you pull the card, you put it back in, you shuffle it up, the probability on the second time hasn't changed because you pulled the card already, because you replaced it. Okay? So this is kind of the idea that we talked about up here. Key idea. The probability of independent events. So if you have 2 events, A and B, and they're independent, then the probability of A and B is just the probability of A times the probability of B, like individually, like separately. Okay, so the probability of ace and king, pulling an ace and then pulling a king on 2 successive draws in that order, is just the probability of pulling an ace times the probability of pulling a king, because they have nothing to do with each other. They're independent events. Okay. Now, one thing I wanted to point out is that we actually use that notation in more than one context. In this context, what we're talking about is 2 trials. So when you're talking about independent events, or what we're going to talk about on the next page, which is dependent events, the key idea is that we're talking about separate trials. It's not the same trial. Now, sometimes this notation can mean something different. Okay, so imagine if A is rolling a 4 and B is rolling an even, or something like that with dice. So sometimes you can get 2 things happening in one trial. Like you can roll a 4 and an even in one trial, and that's kind of a different situation. So with independent and dependent events, which we'll talk about on the next page, keep in mind that we're talking about 2 separate trials, and this is getting A on the first trial and then getting a B on the second trial. Okay, let's take a look and practice here. So in this scenario, we have a bag of marbles that contains 9 red marbles and 3 green marbles, which would be 12 marbles total. Find the probability of drawing a red marble followed by a green marble on 2 successive trials, assuming the first marble is replaced before the second draw. So these events, or these trials, I guess you could say, are going to be independent because the first one's not going to affect the second one. If I pull a red marble on the first try and put it back, it's not going to affect the probability of pulling out a green marble. So what we would write is the probability of red and green. Sorry, that's a D right there. I just almost made it into a G. Red and green is equal to the probability of pulling a red times the probability of pulling a green. Again, because these events are independent events. So the probability of pulling a red, since there's 9 of them, is 9 out of the 12 total marbles. Put the marble back, reset everything, shake the bag up or whatever. Now the probability of pulling a green is 3 out of 12 because there's 12 marbles again, and there's 3 green ones in there. If we simplify the fractions first to make our multiplication easier, we're going to get 3 out of 4 times 1 out of 4, which is 3 out of 16. There's a 3 out of 16 chance there. So again, it's kind of like the fundamental counting principle on the top to figure out how many ways there are to pull a green and then a red and then a green, and then a 12 times 12 on the bottom to figure out, well, what are just all the different possibilities. So you could think of this as 9 times 3 over 12 times 12. If you do it that way, you're going to get 27 over 144. There's 27 ways to pull a red then a green. There's 144 ways to pull 2 marbles, but that's going to simplify to this 3 over 16. The same thing. Okay, second thing, same idea. 2 independent events. Consider an experiment where you first flip a coin and then you roll a standard 6-sided die. What is the probability of flipping a tails followed by rolling a 3? So that would probably be the probability of tails and 3, which would equal the probability of tails times the probability of a 3. Well, for the coin, there are 2 options, heads or tails, and tails is one of those 2 options. For the die, there's only one way to roll a 3, but there's 6 possible outcomes. So you're just going to multiply these 2 separate probabilities and you're going to get 1 out of 12. If you think about all the possibilities for flipping a coin and rolling a die, there's heads 1, heads 2, heads 3, heads 4, heads 5, heads 6. And there's tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. That's 12 options. And tails 3 is one of those 12 options. So you can kind of see it that way as well. Thinking about, well, what are all the different ways you can, flip a tails and roll a 3? There's only one combination of those out of the 12 different combinations. Okay, so that's independent events. On the next page, we're going to talk about dependent events, which is where the first event does affect the second event. Okay, so if one event does affect the probability of another event, then the events are dependent, which changes things a little bit. So let's go back to our card scenario, and this time we're not going to put the first card back. So going back to our card drawing experiment, for 2 consecutive trials of drawing a card from a standard deck of 52 playing cards, if we don't replace the first draw, then the sample space changes for the second draw because there will only be 51 cards to choose from. So you pull the first card, whatever it is, and you don't put it back in the deck. Now there's one less card in the deck and there's only 51 options. Additionally, if we drew a king on the first draw, there are fewer possible outcomes for drawing a king. Right? If the first one you draw is a king and you don't put it back, you only have 3 kings to choose from instead of 4. So the outcome of the first event is going to affect the probability of the second event. It's definitely going to change the possible options of cards you can draw, and it may change the possible outcomes for the event you're looking for as well. It could change the top number or the bottom number of your probability. The probability of drawing a king on the second draw is conditional on the outcome of the first draw. So we have these 2 words, conditional and dependent, and they kind of are used in the same similar situations. The events we call dependent. The probability we call conditional if the events are dependent. So, one more time. If the events are dependent, that means the probability of the second event is conditional on the first event. Okay. All right, there's some new notation here. and kind of a new key term. So conditional probability, how that's defined is the probability of an event B given that event A has already happened or already will happen, right? The probability of drawing a king assuming we've already drawn an ace or something like that. So this is the notation, P for probability. We got the kind of the parentheses like function notation, but this is read B assuming A or B given A or something like to that effect. So the probability of B assuming A is how I would read that. Now, if you look at this formula here, this one we actually already have. This is the probability of independent events, and that was kind of what we had over here, right? This thing right here. But that changes a little bit if the events are dependent. So notice that these formulas look almost the same, except that this one has an extra letter. So this is the probability of A times the probability of B. This is the probability of A times the probability of B assuming that A already happened. Because remember, this event affects the probability of B. Let's look at a real scenario because that's a little bit abstract right now. Let's try to make it a little bit more concrete. All right, so if event A is drawing an ace on the first draw and event B is drawing a king on the second draw, and assuming the first card is not replaced, let's find a couple things. Okay, so this is the probability of B assuming A, or in our situation here, this is the probability of drawing a king given that the first draw was an ace. Okay, well, normally there's 4 kings to choose from in a deck of cards, right? And if we drew an ace on the first one, the number of kings hasn't changed. There's still 4 kings in the deck. What has changed, though, is the sample space, or the number of items in the sample space, because I don't have 52 cards to choose from anymore. If I pulled that first ace out and I didn't put it back, I have 51 cards to choose from. There's still 4 kings, though. So this is the probability of pulling out a king, assuming that you already pulled out an ace. In this scenario, the probability of A and B would look like this. It would be the probability of pulling an ace and then pulling a king. But since those events, pulling an ace and pulling a king, and we're not replacing the original ace, since that first event affects the probability of the second event, we're going to have to use this idea here. So we want the probability of pulling an ace times the probability of pulling a king given the first pull was an ace. So we already have this second piece, we just need this first piece as well. So the probability of pulling an ace is 4 out of 52. The probability of pulling a king, given that we already pulled an ace out, is 4 out of 51. So notice how this one is slightly different from what we did over here on the first page. Right here was 4 out of 52 times 4 out of 52 because we replaced the card, which means that these events were independent. They had nothing to do with each other. The first one didn't affect the second one. So we have this idea. Okay, in this scenario, the only thing that we changed is we didn't replace the first card. And so we have to change the second probability. It's not 4 out of 52 anymore, it's 4 out of 51. Because again, we're assuming that this ace that was pulled isn't getting put back. Let's finish this up. Okay, so on the top we're going to have a 16, 4 times 4. And the bottom is going to be a little bit smaller this time. This time it's 2,652, and that will simplify to 4 over 663. All right, again, notice this probability here, 4 over 663, is different than the probability we calculated over here on the first page when we made those events independent. That's why there's kind of 2 different ways to think about this. Are your events independent or dependent? Your probability is going to change. All right, let's look at a marble example. Now, this is my bad, because this was a first draft. I hadn't worked out the kinks. There needs to be a not in here. We want to change the scenario so that we're picking a marble and we're not putting it back, which would make this scenario dependent events instead of independent. So other than that, it's the same as the previous one. We have a bag of 9 red marbles and 3 green marbles. We're going to find the probability of drawing a red marble followed by a green marble. This is going to take a minute, sorry. I'm recording a video.
Oh.
So.
Are you going to be here tomorrow?
Yeah.
You want to go lunch?
Yeah. Everybody, Mr. C just came in, so that's why. Say hi, everybody.
Hi, everybody. It's my birthday tomorrow, too.
Hot dog.
It would be awesome to have a birthday lunch.
Okay.
With you and Kim. So, okay.
See ya. All right. Sorry for the interruption. Mr. C just dropped by. So that's he's cool. Okay, back to probabilities. So we got the same 9 red marbles and 3 green marbles. We want to find the probability of drawing a red marble followed by a green marble on 2 successive trials, assuming the first marble is not replaced. So that's what we needed, the not replaced before the second draw. All right, so what we want is the probability of red and green. And remember, in this context, that red and green, we're talking about 2 trials, so it's pulling a red followed by pulling a green on the 2 successive trials. Okay, so this is going to be the probability of red times the probability of green assuming red, or pulling a green assuming that the first pull was a red. So again, this is going to change things slightly from the last time we did this problem. Okay, the probability of red is still 9 out of 12 like it was before, but the probability of green assuming red, there's 3 green marbles to choose from, but if we chose a red first and we didn't put it back, there's only 11 marbles to choose from now. So we got 9 times 3, which is 27, over 12 times 11. I shouldn't need a calculator for that, but here we are. And then we're going to simplify that if possible. So it looks like that comes out to 9 over 44. I guess it would have helped if we simplified this fraction first, but yeah, 9 out of 44. Okay, again, notice this probability, 9 out of 44, is different than when we did this problem number 4, which was 3 out of 16. Again, because originally we put the marble back and the bottom number was a 12. But this conditional probability changed the sample space, the number of possible marbles to choose from. Okay, one other kind of question that we can talk about when we talk about independent and dependent is how can you determine if events are independent or dependent? So let's go back to this from the front page again, and you'll notice that this says if and only if. Okay, what that means is that this statement actually goes both ways. So you can think of it like this. If A and B are independent, then use this formula. But you could also think of it the other way, and you could say, if this formula works, then the events must be independent. So if and only if is kind of like a two-way arrow where it says, like, you can go either way. If independent, then use this formula. If this formula, then they're independent. So we can actually use this as a test to see if events are independent. If the probability of A and B is equal to the probability of A times the probability of B, then the events are independent. Let's use that over here. Okay, so we have the probability of A, which is 1 over 4, and we have the probability of B. Now, these events, we haven't defined what the events are. We're not saying it's a card, we're not saying it's a roll of the die or anything like that. We're just saying it's some random events that we don't know. But we're given this information that the probability of A and B is equal to 1 over 10. So if these events are indeed independent, then what should be true is that the probability of A and B should be equal to the probability of A times the probability of B. If this statement is true, the events are independent. If these statements are not true, then the events must be dependent, and that's kind of what we're going to do with our test here. So probability of A and B was 1 out of 10, 1 over 10. Probability of A is 1/4. Probability of B is 2/5. So if I were to multiply on the right-hand side, I'm going to get 1 times 2, which is 2, over 4 times 5, which is 20. And since 2 over 20 simplifies to 1 over 10, this is actually a true statement. So this is actually true in this case, which means these events must be independent. Okay? So it's kind of like, you know, in this situation here, we had 4 out of 663. And in this very similar situation, we had 1 over 169. So it's kind of like, which P of ace and king are you talking about? Are you talking about the independent version, where you get this number? Or are you talking about the dependent version, where you get this number? So they're giving you basically the probability and just making sure that it all lines up. And if it does, according to this formula, then we're talking about independent events. All right, last idea here, which also concerns conditional probabilities. Okay, this is called a two-way table, and it's a way of displaying data. So over here we have a category. This would be like class. And over here we have a category which is gender. And then there's these things called frequencies. So frequencies are just counts. So this 10 represents like how many sophomore girls there are. This is how many sophomore boys. This is how many junior girls and junior boys, how many senior girls and senior boys. So frequencies basically means counts, or how many times that category occurs. So if we are given a two-way table, sometimes they're given with totals, row and column totals, and sometimes they're not. In this case, we don't have those, so the first thing we want to do is find row, column, and table totals. So if I have 10 sophomore girls and 10 junior girls and 10 senior girls, the question is, how many girls do we have in total? So if I do 10 plus 7 plus 9, that's 26 possible girls in this scenario. Okay, we can also total up the boys. We have 13 sophomore boys and 4 junior boys and 5 senior boys. Putting those all together, you're going to get 22 boys. We can also total in the other direction. So we got 10 sophomore girls and 10 sophomore boys, which means we have 23 sophomores total. We have 7 junior girls and 4 junior boys, which means we have 11 total juniors. With seniors, we got 9 girls and 5 boys, so that's 14 total. If I add the 23 sophomores, the 11 juniors, and the 14 seniors, that is going to give me 48 total students. And likewise, if I add the 26 girls and the 22 boys, that will also give me 48 students. So whether I total this way or this way, I get the same table total. So we got some row totals, we got some column totals, and we have the table total right here. The reason why those totals are important is because if we're talking about probability, we need to know how many possible outcomes there are. So let's find some probabilities here. Okay, we have a bunch to find out. A is the event randomly selecting a student that's a girl, and B is the event randomly selecting a student that's a sophomore. So what's the probability of A? What's the probability of randomly selecting a student that's a girl? Well, you got to think about how many ways there are to choose a girl. There's 26 out of all the possible students you can choose from. All right, there's 48 students total to choose from. So if we simplify this, we're going to get 13 over 24. Okay, let's do the probability of B. Randomly selecting a student that's a sophomore. So we pick one of the students. How many possible sophomores are there to pick from? There's 23 total sophomores out of those 48 possible students. So 23 is prime. We can't really go any further than that because 23 is only divisible by 23 and 1. But there's our probability. Okay. Now what we have is we have these conditional probabilities. So that's our new notation. This is the probability of A assuming B. So this is the probability of girl assuming sophomore. So this actually changes the sample space, right? If you're talking about you're assuming that the girl is a sophomore, you don't have to consider any students that aren't sophomores. So what this does here, this assuming sophomore, basically narrows your focus to only looking at this row of the table. So how many girls are there to choose from this row? There's 10 sophomore girls to choose from out of 23 total sophomores. So notice that the sample space here is different now, or the size of the sample space, I guess I should say. The number of outcomes in the sample space is different because of this part. We're assuming we already are talking about sophomores. So, yeah, that doesn't simplify. Okay, now we got the same two letters, but the order that these are written in actually makes a difference. This is the probability of sophomore, given that we already know it's a girl. Okay, probability of sophomore given girl. So this narrows our focus to just looking at the girl row. We're only concerned with girls. We're already assuming that we have a girl, that we're talking about a girl. What's the probability that it's a sophomore given that we already know it's a girl? Well, there are 26 girls to choose from, and there's 10 sophomore girls out of those 26 girls. Right, so that's 5 out of 13. So notice that here I started with a table total and a table total. Here my total number of possibilities was a row total, and here it was a column total. So the conditional probability narrows your focus to, one row or one column. Okay. Let's actually do 13 first, and then we'll come back and do 12, because this is actually part of 12, and I probably should have ordered them a different way. All right, now this is a little bit confusing, because we used this notation before, probability of A and B. In this context, I'm telling you it's a single trial. So the thing that's a little bit confusing sometimes is trying to ask yourself, is this one trial or is this two trials? So when it says probability in A and B, or in other words, the probability of girl and sophomore, before we can answer that question, we have to know, is this like choosing a girl first and then choosing a sophomore? In other words, two separate trials? Or is this choosing one girl and trying to see if she's a girl and a sophomore at the same time? So in this context, what we're talking about is one trial, choosing one girl and seeing if she's also choosing one student, and what's the probability that she's both a girl and a sophomore at the same time. So if we look at our table, we're choosing one student. We haven't narrowed it down to a specific column or row here. It's just one possibility. So we got 48 students to choose from. Okay, this total, sorry. And the probability that she's a girl and a sophomore would be this. This is the number of people who are girls and sophomores. There's 10 sophomore girls. So the probability that you chose a sophomore girl is 10, because there's 10 of them, out of 48 students. So that's 5 out of 24. So again, you got to be careful with this phrase, because it kind of, we treat them differently if this was two separate trials versus if it's one trial. And in this case, we're talking about one trial. Okay, now let's go up and talk about 12. Okay, so now, again, this is a single trial. What is the probability that we choose a student that is either a girl or a sophomore? Okay, so let's take a look at that. Based on what we talked about in our last lesson, these are inclusive probabilities. So we have the probability of girl or sophomore, which is the probability that it's a girl, plus the probability that it's a sophomore, But if you think about that, we just double counted the sophomore girls, right? I'll explain that in a second. But what we're going to need to do is we're going to have to subtract the probability that it's a girl and a sophomore. In other words, it's a sophomore girl. Okay, so let's kind of unpack that a little bit. Okay, the probability that I got a girl, we already knew it was 26 over 48. There are 26 girls out of the 48 students. So the probability of choosing a girl is 26 out of 48. Okay. The probability of choosing a sophomore is 23 out of 48 because there's 23 sophomores out of 48 students. But if you think about what we just did is we counted the 26 girls and we're adding that to the 23 sophomores, and we just double counted the 10 sophomore girls because we included those 10 in our total number of girls and we included those 10 in our 23 total sophomores. So we just double counted the 10. Okay? So what we need to do is we need to subtract out the 10 sophomore girls so that we don't double count them. So probability of girl plus probability of sophomore minus the probability that it's a sophomore girl. So this 10 out of 48 is the same 10 out of 48 we were talking about down here. All right, so 26 and 23 together, that's 49. Take away 10, that's 39. They all have a common denominator, so I can do that. And then 3 goes into both of these, so that would be 13 over 16 as our final probability. Okay, so again, a little tricky on this context because it's not always clear unless somebody tells you when you're doing these guys, if you're talking about one trial and you want to get both outcomes or one or the other, or if you're talking about 2 successive trials. And in this context, when we're working on the two-way table, we're going to assume that we're talking about one trial or one choosing, just to make it clear. Okay, so that's how you kind of read a two-way table and calculate some probabilities using a two-way table. Thanks for watching.